there's a Boolean flag, right? And what does that Boolean flag do? It basically says, is it the first element or not? If the first element, we just return the seed, we don't apply the Boolean function, right? After the first element, we set this flag to false, and then subsequently, since the flag is always false, we always apply the function and then return the result. Okay? Now, there's nothing wrong with that, except that if you have a very long list of, let's say, 1 million elements, the first time is going to be, say that it's the first time, and then subsequently for the rest of the 99999 time is going to be false, right? So we are doing this additional check all the time. So this code that we give you for this recitation has a very neat way of getting around that problem. Okay? And that is this chunk of code over here. Okay? So there is a func, a member inside this anonymous class called func, which is initialized to this funny looking lambda. Okay? And not only that, within this lambda, we actually update func itself to something. Okay? So let's take a look at this and try to understand what exactly is going on here. So let's look at this func here. So this func is lambda. So in other words, it's an anonymous class, right? So you see here, this is an anonymous class within an anonymous class. Okay? The other is an anonymous class. This is another anonymous class. Now let's trace through what happened when I call get on this data source, on this infinite list that we create through the iterate method. The first time we call get, right? The first time we call get, we're going to call func apply element. Right? Func apply element. So what is this func? Now, this func here is this func that we define here, right? So the first time we call, right, this one is actually pointing to this. This is actually pointing to this lambda. Okay? So when we apply this to an element, we are basically executing these two lines of code. Right? We apply this lambda, so basically we are executing these two lines of code. Now what does these two lines of code say? It basically says, right? Point func to next. Okay? So this means that after you execute this code, right, your func is going to, instead of pointing to this strange lambda here, is going to now point to next. Okay? And then it's going to return element. So what is element? This is the first time we call, right? So element is just seed. Right? So in fact, we could easily write this. We could easily write this as just return seed. It's the same. Okay. So we have this func initially point to this lambda here the first time, right? So the first time we call this lambda is going to return seed, just like what we want. Okay. Now the second time onwards, func has been changed to point to next already, right? Point to next already. So now subsequent, calls to get this lambda is not going to matter anymore, right? This function is going to point to next, and then every time we call func apply element, it's just the same as next apply element. So this is what we want. Right? So this little chunk of code here basically say, the first time I just return the element. So I sort of have a customized function for the first call only. After that, I set my function to point to something else, and then I'm just going to call that function subsequently. Okay. So you understand the mechanism? Yeah. Okay. Now this is something very powerful as well, because what you see here is that you can change the behavior of your code during runtime. Right? In case you don't realize it. So this is a function, right? This line of code remains the same. This line of code remains the same, right? But which code it executes, whether it executes this function here or execute this next here, depends on what you point this function to during runtime. Okay? So during runtime, you can have a bunch of code that call this, and then maybe certain condition is true, then you point your function to another function, and then the code continues executing. But now it's executing something else because your function is pointing to another lambda, right? And then execute somewhere certain condition happens, then you point your function again to something else. Right? So now the same line of code you can execute different things, compute different things on demand. Okay? So this is a very, very powerful concept. Something that you can do with lambda, but not as elegantly. You can do it with other things as well, like objects and so on, but not as elegantly as this. Okay. So this is just to explain the first interface that we show you on the first page. We haven't get to the question yet. So now let's get to the question. So the question says, modify the iterate method such that it now supports the condition to stop iterating. Okay, so if you look at this iterate over here, it takes in the seed, right? So I can do ifl dot iterate, I say 0, and then I take in a function, right? So I say x arrow x plus 1, right? That's standard example. Now there's no way to stop this, right? So in the lecture we show that you do iterate 0, x plus 1, right? This actually doesn't do anything, but once you do for each, then it's going to consume the elements, and it's not going to stop, because this is an infinite list. What the question asks us to do is to add a condition here. So you can say I start with 0, I want x to be less than 3, and then x equal to x plus 1, for example. Right? So this is very similar to, actually exactly the same as for loop, right? So how do you write for loop? You write for I equals to 0, I less than 3, I plus plus. Okay? So now we're just going to do the same. We're going to do iterate. Right? 0. Now it's just that instead of condition, I put in a predicate, a lambda expression. Instead of this expression, I'm just going to put in another lambda expression. Okay? So this is what we're going to do. Right, so we're just going to stick this predicate. Before I continue, I just want to make sure everybody understands the ordering of this lambdas here. In the morning, there are some confusions about how for loop works. Okay. Now, for loop should come very naturally to you, right? So after you've gone through 10 and maybe even 30, 40 and other programming courses. But for some reason, when we ask students this, some students get stumped for what should be the right order of execution. And not only that, we see that on Piazza, many of you who did your lab 7, right, you run into this problem as well. So if your lab 7, when you pass your level 5 or level 6, the last customer is missing, right? If the last customer is missing, then most likely you run into this bug that I'm going to show you. Okay. So let me ask you this. So if I have a for loop for I equals 0, I less than 3, I plus plus, what's the order of execution? Well, first thing is that you do I equals to 0, right? Initialize. What's the second thing that you do? Check. Very good. So you check whether this is I is less than 3 or not. After that, you enter the loop, right? You go into the loop. After, okay, sorry, not like this. You go into the loop. So this is the body of the loop. After you go into the body of the loop, what do you do next? You come back to check, or come back like this to check, or you go add. Right, you go add. So this would be the after you add. So you add first, and then you check. You add first, and then you check. Right. In other words, we are going to do I equals to I plus 1 first, right? Before we check. We're going to do the function first before the predicate. Okay. Now, what happened to the value that you get from next if this predicate is false? I repeat my question again. What happened to this value if this predicate is false? Right. So you say I equals to I less than 3, right? So you do I equals to 0 plus 1 become 1 become 2 become 3, 3 not less than 3. Okay, so you stop. What happened to that 3 that you add just now? Throw away. You are not using it. Okay. So now let me get back to the part. So many of you use scanner in using iterate for your lab. So what do? You scanner as next. Scanner has next. Here, this is your condition. And then here what you do scanner dot I forgot what's it called, get next, right? Get next in or get next double. So what's the order? You get first and then you check whether you still have any more elements or not. Now if you get a double value and then you check, hey, this is the last value, no more element. What happened to the last value that you get? You throw away. So that's why some students are missing this, they miss the last optional in their code. They use iterate to do the scanning. Okay? So if you have this problem, go back, or you see your friends having this bug, just tell them about this problem. Right? You always apply the function first before you check the predicate, and if the predicate evaluates to false, right? Then evaluate to true or false. If the function evaluates to false, yeah, then you throw the things that you read away. Okay. So this is the mechanism of iterate. So now let's get to the code. Okay, so I already have my predicate here. And now I just need to get in my get, I just need to check the predicate. Now, should I check before I apply or after I apply? What did we say just now? Just now we said we apply the function first, then we check the predicate. Right? So I apply first and then I just say predicate of test, element. If this is true, right, then I'm just going to return my element just as usual. Otherwise, now this is the part that's a little bit tricky. If I get the element at test, and then it turns out the condition is not fulfilled anymore. Right? The condition returns false. What should you return? Empty. Good. So you return optional empty. Okay? So this means that if I see something empty, then it means that I have reached the end of my data stream. Okay? Now let's look at the rest of the implementation here and see how this thing affects. Now how about map? Map I get from my upstream, I apply method. Now if I get something empty, optional empty, does it affect this line? It doesn't, right? Because optional takes care of whether something is empty or not false. So we don't have to change this line. What about for each? For each, now we have an infinite loop, right, that keeps getting the item. So we have to change this. It shouldn't be infinite anymore, because we might see an empty object. If we see something, if I see an empty optional, then I should stop, right? So I should continue if while current is empty, while not current is empty, right? While current is present, is the same thing. While current is present, I just call the action to consume the item, and then get, and then keep moving. Okay. So this is version 1, the simple version of the solution. Everybody get this? Now there's a problem with this one. The problem is that we are using optional empty to tell us whether we have reached the end of the string or not. Now what could be wrong with that? What could go wrong? Remember on Monday when we talked about filtering items, right? We said when we filter things, if things that doesn't pass the filter, we want to throw away. How do we throw things away? We replace that with an optional empty. Right? Or it could be that the string itself, the infinite list itself, is generating optional empty. So optional empty is not the robust way to check whether we have reached the end of the string or not. So, but the logic is still the same, so I won't code up everything for you. I'll just show you what we can do. Okay. What we can do is we keep a Boolean flag that says whether we have reached the end of the string or not. Okay? And when we really reach the end of the string, we set this flag to true. As simple as that. Okay? When we set the flag to true, and then we just have a function check whether it's reached the end of the string or reached the end of the list, and then just return it. Okay? Simple, right? Just add a flag. Now what about map and for each? For each is the same. Okay, let me comment this up. So you can just do while not the end. While not the end, then you just do your stuff, right? Just as before. What about map? Now map, we have to check whether we have reached the end or not. Okay. So one thing you can do is you call to check whether the string has reached the end or not. You call the end method of the calling class. In this case, I say you iterate map, then you call the end method of the iterate. See whether we reach the end or not. Okay. You can even implement this. You say, okay, if ifl implement dot this dot the end, right? Then you say the end equals to true. Else, then you apply the method. So here you return optional empty. Okay. So the end equals to true, and then here you just return the end. You can also do this. Then you save on mapping if you are doing save on mapping operation if you already reached the end. Okay. So basically just add a flag and then just tweak all the logic to make sure that you check that flag whether we reach the end of the string. Okay. Now let us look at the part B of this question. Okay. So in part B of this question, you are given this code, right? IFL iterate 0, x less than 2, and then your x arrow x plus 1, you map F, you map G, and then you call for each C. Okay. Now here I actually take up E, I put another function here, E, and for E, F, and G, I just make up some function values, and then, but what is more important is I add a print statement. I try to print out what each of these functions is doing. Right? Or I print out which function is getting called. Okay. So now if I want to know what is the sequence of execution, right, then I just run the code and then I can figure out, oh, the sequence of call is FGCE, But of course, this is an exam question. During exam, you can't write a code to test on. So you have to understand the sequence of calls that will lead to this execution sequence of the lambdas. Okay. So now let's look at this carefully. Okay. Let me hold this. Okay. Let's look at this one carefully. Now, remember we are talking about lazy evaluated list, right? And here, when I iterate to generate things, nothing actually gets generated until somebody calls get on the iterated object. And same thing with map, right? When I call map, I basically just create an anonymous class, put it in the field. Only when somebody calls get, then the action happens, right? Same thing with map. Now for each actually doesn't create a new class. For each actually goes into the loop and start to get stuff. Okay? So for each is a terminal operation, and it is the one that is triggering getting things from the upstream. Okay? So for each, we'll try to get from here, from this object, we will try to get from this object, we will try to get from this object. Now, when they try to get things, do they execute the lambda? No. Right? So let's go back to the code. Right? Let's go back to the code here. So this is the map. This is the for each. Now, for each, you will call get first without invoking the action. This get will call this get for the map. When you call the map, you will call get. Okay, and since I have two maps, right, this get again will call this get, and then we'll throw implement of this dot get, and now finally this get, since I have for each map iterate, right? So now you will go from map to map now to iterate. You will go to this get. But remember, just now I traced through the code, right? The first time I call the get, I'm not actually applying next. I'm actually applying this internal weird lambda that I have here, which returns me the seed. Which makes sense because in the first time I call this, right? I just take the seed now. I don't need to evaluate my expression. So the first time I call this, I will just get the 0. So this 0 will be returned to the first map call. Right, they return to the first map call. So this value here will return 0, and now I will call map on this optional of 0. So the first one that is called is f. So I call f first. After I call f, I return. Right, then this one will return f of optional of 0, right? And then I'll call map, the second map is called G. Okay? And then I will return G of f of option 0 to here, and then I go into my loop, right? I go into my for each loop, and then if it's not the end yet, then I will call my action regime C. So that's how I get F, G, and C. Okay. So remember, when we do this, we always go upstream, downstream, upstream, downstream, right? Now, it's just that when we go upstream, we are just get. We try to get from the data source. And then when we go downstream, we actually apply the function, right? Map, filter, limit, whatever, until we reach the end. And then we go up again, right? Then we go one more round down, okay? So now we have gone one round up and down, F, G, and C. And then since this is a loop, we are going to go back, right? Oh, sorry. Well, after applying C, we are going to get another one. We're going to get another one. So again, we go up. We're going to go up to from for each to map, to iterate. And now I have already used up my 0, right? So now I have to apply my E to generate my next number, which is 1. So you'll go up, generate the next number. So now you will call E. And then you will go down, go back down again, F, G, C. And then you will go up again, you will call E again. But let's look at the code here. This time, since I want to stop at x, x less than 2, I got 0, 1. The second time I call E is going to generate 2 already. Right? So we get 2, it doesn't pass the filter, so we throw 2 away and we stop. Stop meaning I pass optional empty down to here, optional empty down to here, and then down to for each. And when optional empty pass through the map, nothing gets called. Right? Until we read for each, although for each nothing gets called also because we are exiting the loop already when it's empty. Not this version, but the version after I change. Okay, so this is the answer. And if you are still confused, go back, trace through the code again, make sure you understand this flow of execution. Okay. So as an additional exercise, we also ask you to write a concat method. Okay. So the concat method basically takes in two infinite lists, and then just concatenate them together. Meaning that you're going to return a list, start with all elements of this one first, followed by all elements of this two. Okay. And I already have some of the template filled up here to save time, but the idea of the code is very simple. So I'm just going to check if we have reached the end of this one. If not, then I just return this one dot get. I keep getting things from my first list. Keep getting until I reach the end. Right. Then if I reach this one, the end of this one, then I start to get from this two. Keep getting until we reach the end of these two. Right? If both this one and we have reached the end of both this one and these two, then I just set the end equal to true, and I just return option 9. That's all. Okay, nothing fancy, but you just have to keep in mind that the purpose of the get function is to get one element. Now, common mistake for students is that, concat, so write a for loop. Right. But no, remember we are calling get one at a time because we want to be lazy. We don't want to go through the loop, get all the elements. So this is the implementation for concat. Okay? Now, I will now move on to question 2. Now, question 2 is also a past year exam question, and I think this is a really nice question. I didn't set this, I think Henry said it last year. It actually shows another use of lazy evaluation, and for this particular case, we are going to use lambda and the fact that it's lazy evaluated to mimic how we make recursive calls. Right? And in doing that, we want to get around some of the some of the problems related to Java implementation. So let me explain what I mean. So we are given this recursive function. Right? I think all of you should be familiar with recursive calls, recursive functions. Now here I just have a sum, I take in the n, and then I just recursively call sum again with a smaller n. And as I recurse down with smaller and smaller n, I accumulate my result. Right? So I say n plus result, n plus result. So I keep accumulating my result until I reach the n, and then when n goes to 0, I just return my result back. Okay? Now this is a special type of recursive function. And the name for this is that this is a tail recursion. A tail recursion means that in the return statement of the function, there is nothing else but calling itself. Nothing else but calling itself. If I do return sum versus plus 1, then no, it's not a tail recursion anymore. Right? So in tail recursion, it must be, the return statement must contain nothing else but a call to itself. Okay? Now let's trace through the steps when we call this function recursively. Right? Let me start by calling sum of 6 and 0. Okay? So I start with the first stack frame. I have 2 variables. I have n, which is 6, right? And then I have result. I use r as a short form, which is 0. So this is my first call. Right? So n is not 0, so I'm going to call sum again. Now this time I'm going to call, this is my first sum. Right? I'm going to call sum again. This time I'm going to call it with n equals, okay, maybe 6 is it too many. I start with 3. 3. Okay. So I start with n becomes 2. The result r becomes 3 plus 0 becomes 3. Right? And then I'm going to recurse again. N is 1. My result is, right? My result is 5. Right? And then we're going to recurse again. N is now 0. R is now 6. And then I'm done. Right? So I keep recursing. Recurse. Oh, base case. When I reach base case, I just return the value. Right? Base case, return value. Now you see that when I return this value, I return 6. Normally you return from this frame to the previous one, right? You return 6 to the previous sum. Now normally when you return, like sometimes you write recursive call like this, like you return and then you do more computation. Let's say just now plus 1. So you return 6, then you plus 1. Then you return and you plus 1. If you do that, then it's not tail recursive anymore. But this is the version without the plus 1. Right? So the only thing that I return is 6. And the important thing is that this 6 get returned all the way to the top. In other words, when we make this type of recursive call, we are building up everything on the stack, one after another. But when we return, we are not doing anything useful. Right? So all these things on the stack are actually useless. Right? Or actually useless. We could easily just take 6 and then just return it to here. Right? Because of the tail recursion, we can do that. Now, in other programming languages like C or Scala or other programming languages, they optimize the tail recursion. So optimize means that when they compile the code, they say, oh, this is a tail recursion. So when they generate the assembly language, they don't build up the stack like this. They build up only one stack. After 0, 3, when you call when you make the second call, right, this one actually removed, right? When you make the third call, this one is removed because it's not useful, right? Your third call, this call is removed. So make this call is just returned. So it avoids the problem of putting up so many useless things on the stack. Now, for some unknown reason, Java doesn't do this, right? Java doesn't optimize the way the tail recursion. And because of this, if you try to run the code just now with a number that's too big, you will get a stack overflow. So let me show you, right? So I have the recursive version of the sum just now. I could call it recursive sum. Okay, and now if I load this in JShell, call summer as in the code that from sum, recursive sum, I can do 10, right? Okay, 10, 0, no problem. 1,000, no problem. 10,000, no problem. 100,000, boom. You get stack overflow. Now you have thousands and thousands of frames on your stack. Without stack overflow. But all these things on the stack are useless. Okay? So we are going to see how we can optimize the way that all the user stack frame in Java ourselves. Right? JVM doesn't want to do it, Oracle doesn't want to do it, we do it ourselves using lazy evaluation. So this is the code that is given. Okay? So now let's spend some time and try to understand what this code is doing. We have a compute class. Right? This compute class actually represents a certain computation that we want to compute. And you can see from this code that we can return a new base or a new recursive as a type of compute. So what does this mean? This means that base and recursive must be a subtype of compute. Okay. Now let's look at this code here. This code is actually very similar to our sum, right? If n equal to 0, return the result. If n is not equal to 0, I recursively call sum. Right? It's just that now we have all this a bunch of stuff, a bunch of other symbols around, but the logic is still the same. Okay. Now, this is the part where we create this object that represents the computation. This is the part that is actually making the recursive call. Now remember what I said just now about how we are making recursive call, right? We just keep recursing until we reach the end, the base case, then we return the value. Right? That's how recursion call works. Now, what you look at this code here, while it's still recursive, you just keep recursing until it's not recursive anymore, then you return the value. It's exactly the same. So, in other words, this code over here is simulating or mimicking the recursive process of calling functions. Okay. So we start with by creating